Welcome everyone to the water and irrigation session. So we have presentations for representing a good combination of regions, including the United States. I believe Srabashi will present something she's recently doing pretty exciting about looking at the impact of conservation policies on the labor market. And then we have Ruiying from Zhejiang University presenting something about China. And then, so finally we have Alla presenting water modeling paper in the West Asia region. And because Srabashi just came in and need some updating of her software, and so we let Ruiying go first. And Ruiying, if you can share your presentation with us.
Okay. Oh, can you see my screen?
I'm not seeing it. How about everyone else?
Sorry, I need.
Yeah. Okay. Can you go full screen? Yep. Looks good. All right. The floor is yours, Ruiying.
Okay. Hello, everyone. Thanks, Jing, for the introduction and for holding the session. My name is Ruiying. I'm a PhD candidate of Department of Agricultural Economics and Management at Zhejiang University. Today, I would want to introduce a working paper. The title is Enhancing Total Factor Productivity in China's Crop Production, Contributions to Food and Environmental Security. I will introduce the following parts: the introduction, methods, the results, and the conclusion. As we all know, China is the most population country in the world. The increasing food demand presents a great challenge to agricultural production. However, the production in China is constrained by both resources and the environment. So, increasing agricultural total factor productivity is particularly important as it is an efficient measure to ensure food security and reduce the negative impact of agricultural production on the environment. Improving production with lower environmental costs in agriculture is also a key step for China to achieve the Sustainable Development Goals. In the previous studies, the importance of projection of future agricultural productivity is widely recognized. A strand of literature finds the important role of technological change in improving agricultural productivity and implements TC endogenous. The TFP growth in the future has also been found varies under different scenarios and has impact on food price. Although these studies provide us with a lot of information in the prediction of TFP, they are mainly focused on global level. There is still a lack of research on forecasting China's future agricultural TFP. Because existing researchers relevant to China's agricultural TFP mainly focus on the calculation of TFP growth, factors affecting TFP growth, and the impact of TFP growth. And these researches are based on historical data and have limited forecasts for the future. We need analysis about China's TFP under different scenarios in the future to inform us more information. Hence, this article tries to address two questions below. How will TFP change of China's crop sector in the future under different future socio-economic scenarios? And the second one is, What are the impacts of TFP changes of crop sector on food and environmental security? To address the questions, as the agricultural sector has great adaptability, technological change induced by investment in research and development need to be employment endogenous to avoid serious biases. We combine an agroeconomic land system model with a well-recognized TFP calculation method to measure TFP changes in China's crop sector. Firstly, this study uses model of agricultural production and its impact on the environment, hereinafter referred to as MAGPIE, to simulate the production outcomes based on endogenous TC and different future socio-economic scenarios. MAGPIE is an open-source partial equilibrium model that combines economic and biophysical approaches to simulate spatially explicit global scenarios of land use and the respective interactions with the environment. This study uses the version 4.3.5 of MAGPIE, which includes 12 world regions. The article's analysis of food and environmental security mainly involves modules such as land, trade, water, nitrogen, and the carbon module. The scenarios used in this paper have been developed by researchers and implemented into MAGPIE model. SSP1 refers to sustainable development pace. SSP2 means the middle of the load. SSP3 has regional rivalry. SSP4 is unequal development pace, while SSP5 is high-speed development pace. Secondly, we do poster calculation based on the model output. The data envelope analysis is employed to calculate TFP changes in China's crop sector. We use the aggregated amount of crop commodities as outputs, and the cropland, water use, vector costs, fertilizer costs, and seed are used as inputs. And then we use TFP and the indicators extract from MAGPIE simulation results to analyze the impact of TFP on food and environmental security. This article has 4 main results for now. The first one is about the TFP growth in China's crop sector. Figure 2 shows the cumulative TFP growth in China's crop sector for each scenarios by 2060. The article normalized the TFP to 1 in 2020. The results in Figure 2 reveal that the TFP of crop sector in China will continue to grow but vary across different scenarios. There is the highest TFP growth in SSP5, followed by SSP4, SSP1, and SSP3, while SSP2 has the lowest growth in TFP with an increase of 10.5% by 2060. We further divide the crop sector into 5 crop categories, including cereals, oil crops, sugar crops, tubers, vegetables, and fruits. As shown in Figure 3, the TFP growth is different across specific crop types. Oil crops have the fastest productivity growth, followed by cereals, tubers, vegetables, and fruits, while sugar crops with the latest productivity growth. Since a large number of studies have shown that TFP has a significant impact on trade, we also analyzed China's future trade situation. Figure 4 shows average of net exports of specific crops over time in each scenarios for 3 time spans. Panel A shows the average from 2020 to 2030. Panel B shows the average from 2035 to 2045, while panel C shows the average from 2050 to 2060. With the continuous growth of productivity in crop sector, China has already achieved the net export of some crops. Note that maize, temperate crops, and groundnuts are the main export crops, accounting for 94% of China's crop sector exports. The scenarios of SSP1, SSP4, and SSP5 with higher TFP growth rates would have more net exports than SSP2 and SSP3 in the 3 time spans. And the net exports have increased over time. At the same time, imports are also needed to meet domestic demand due to the distribution of domestic planting structure. Soybeans, vegetables and fruits, and the sugar crops are the main imported products, accounting for 90% of China's crop sector imports from 2020 to 2060. Although China needs to import a certain amount of soybeans, vegetables, fruits, and sugar crops to meet domestic demand in 2060, this import volume will be lower than that in 2020. The third main finding is about the impact of TFP on food security. The growth of TFP in crop sector ensures food security by boosting self-sufficiency and by lowering consumer prices, thereby improving the food availability and food access in China. Figure 5 shows the self-sufficiency and consumer price of crop sector and of specific crop types in 2030 and 2060. Here, consumer prices are normalized to equal 1 in 2020. With the growth of total factor productivity, the self-sufficiency rate of the crop sector will increase, and it will basically reach a state of self-sufficiency in 2030, and the self-sufficiency rate will further increase in 2060. The increase in TFP also brings down consumer prices, a downward trend that is more pronounced in 2060. From the perspective of subdivided crops, the impact of total factor productivity is different. Crop categories with large increases in TFP and self-sufficiency, such as cereals, saw the largest declines in consumer prices. However, although TFP increased considerably of oil crops, sugar crops, and vegetables and fruits, since imports are needed to meet domestic demand, the consumer prices fall less than cereals. The growth of TFP in crop sector is also an indispensable and practical step to respond to changes in the structure of food demand. As we can see in Figure 6, the proportion of livestock products in human food will gradually increase in the future, especially when measured in calories and protein, as almost 50% of feed needs of the livestock sector are met by crop products. The productivity growth of crop sector is of great importance for responding to the increased demand of livestock products. After food security, we also investigate the impact of TFP growth on environmental security. In terms of environmental security, we mainly focus on the water scarcity mitigation and the emissions abatement. Figure 7 reveals the relative changes of TFP, water scarcity, and the GHG emissions into 2060 with respect to 2020. The water scarcity of agricultural water in China can be alleviated namely by 60% in SSP1, 46% in SSP2, 51% in SSP3, 55% in SSP4, and 47% in SSP5. The alleviation of water scarcity is mainly because the growth of TFP gives room for adjustment of crop planting structure and the special planting structure. Figure 8 shows the irrigated cropland of specific crop types in 2020 and 2060. As we can see, rice, temperate crops, tubers, vegetables, and fruits also mass accounted a large amount of irrigated arable land, account for about 93% of the total irrigated arable land. The irrigation water used by these 5 types of crops also accounted for 93% of the crop irrigation water. Given the changes in demand, the acreage of rice, temperate crops, vegetables, and fruits decreased, while that of maize increased. In scenarios of SSP1, SSP4, and SSP5 with higher productivity growth, the reduction in the irrigated areas of rice, temperate crops, vegetables, and fruits would be higher compared to that in SSP2 and SSP3. Likewise, the reduction in water consumption in SSP1, SSP4, and SSP5 would be stronger compared to that in SSP2 and SSP3. But moreover, despite the increase in irrigated arable land, the newly increased irrigated cropland would be mainly concentrated in the areas with abundant irrigation resources due to the adjustment of the special planting structure. This would mitigate the problems of uneven distribution of water resources in China, and most importantly, it can alleviate the acute problems of agricultural water in some areas in China. In terms of emissions abatement, the GHG emissions induced by planting activities are reduced by 29% in SSP1, 17% in SSP2, 10% in SSP3, 15% in SSP4, while GHG emissions induced by planting activities in SSP5 shows a small increase by about 8%. That's mainly because maybe more fertilizer will be used in SSP5. For now, this paper has 3 main conclusions. Firstly, the TFP of crop sector in China will continue to grow, but vary across different scenarios and the specific crop types. Secondly, the growth of TFP ensures food security by bolstering self-sufficiency and lowering consumer prices. Meanwhile, the improvement of total factor productivity of the crop sector is also an important condition for covering with changes in the structure of food demand. Finally, the TFP growth ensures environmental security by alleviating the scarcity of agricultural water and reduces the GHG emissions induced by planting activities. Oh, that's all. Thank you.
Good. Thank you for the very interesting presentation, Ruiying. So let's see if we have any questions from the audience. So while we're waiting, so I probably have a few for you to clarify. So when you are talking about the TFP growth can help save water use for irrigation in China, do you consider, is it just like a input-output kind of saving, or do you also consider the improved irrigation efficiency due to some better equipment? For example, is it changing? Is the irrigation type is changing from like a flooding irrigation to some central pivot irrigation or draping irrigation?
Thank you for your question. I have to say the irrigation efficiency in the model simulation for now is constant. Yeah, so it is not, this paper doesn't consider the different irrigation efficiency for now, but it is a good suggestion.
Yeah, it's better to include some of the details there, at least take a look at the historical data to see if there is a trend showing the technology of irrigation is improving, because we have done some similar analysis in the context of US, and we found that over time you see more water saving efficient, like a water irrigation efficient equipment being installed and used in the US farms. But so your first impression will be, the irrigated sector will be saving some water, but the fact is we're seeing more water is being used over time, although the water saving equipment is continuing to be introduced into the irrigated sector. So there will be a rebound effect. So more in that case. So I see some raising hand from Srabashi. Go ahead, Srabashi, to ask your question, please.
Hi, Ruiying. Thanks for the very nice talk. I have a very similar question to Jing's. So when you say TFP growth, you spoke about you spoke about the crop sector. Do you also mean TFP growth in the livestock sector also? That's one. And the second is that when you talk about GHG saving, can you like disaggregate that into like land use saving? Like if there is TFP growth, there might be like, maybe there is increase in demand, but maybe that increase in demand is met by lesser land than otherwise. And then can you disaggregate that into like land use saving and also like emission saving by livestock? And there's rice seemed like a big portion of cultivation. So rice has a lot of emissions. So can you disaggregate your emission saving into different components?
Okay. Firstly, this paper just focus on the crop sector. So the TFP growth of livestock sector isn't consist in this paper, but yes, we will consider that. We will consider that in the next step. And sorry, I don't listen clearly about the second one. Do you mean the emissions of livestock should be considered in the emission abatement?
So I guess if emissions like if the TFP improvement is not attributed to livestock, so then that doesn't make sense. But I was wondering, like rice is a very large section of that graph that you showed. Rice is a large section of irrigated land that is cultivated, and rice has a lot of emissions in cultivation. So just the biological process of growing rice has a lot of emissions. I understand. So how much of the emission saving is coming from land saving, so conserving land, if that's the case, and how much of it is coming from like emissions by crops, if that makes sense. You don't have to, you can think about it later and let me know. That's also fine.
Okay, thank you.
Yeah, I think one is from the extensive margin. So if you have better technology, you save some land. So there is reduced emissions from the land saving, but also could come from the crop composition. Because
the result I present today of the emission of the emissions induced by planting activities only consist of the CH4 and the N2O. And thanks for the suggestion. I think the carbon sink induced by land use change is also very important, and we should consider it in the next step.
Yeah, thank you.
Okay. And Seymour, Sebnam, and then Fazard. Sebnam, please.
Hello, colleagues. Excellent presentation. So my question is a little bit coming from the policy. If you can, enlighten us, what is the policy behind TFP growth? Is there one, first of all? So is there a public plan looking at, how much the government, let's say, or local authority will spend on maintaining the infrastructure in irrigation? And what is the likely impact on TFP, and also the operation and maintenance, the daily, routine of these systems. I think it has something to do with the TFP growth that you are showing, but I'm not sure how it's working. And the second one, can you also elaborate a little bit more on environmental security when you refer to the irrigation? Is there also a planning behind it that that volume of water will be for irrigation in this locality and the rest will be for other uses? If you may, thank you.
Okay. Firstly, is about the policy implication. I think the investment in research and development is an important measure to improve the TFP. So I think the government should invest more on that. And I don't understand the second questions.
In your environmental security slide, you're talking about GHG emissions, and in your presentation, at some point you mentioned sufficient water for irrigation. So my take on it, are you considering an ecosystem of water use, where some water will be saved for the nature's benefit, some water will be used for irrigation, and the rest will be used by households and industries and energy? Is this what you had in mind, or maybe I didn't get your message?
Okay. Actually, maybe the issues isn't considered in this paper.
Yeah, the slide before that, I think you started there.
This one?
Yes, it says environmental security. So
I think that's
in the slide. We can talk offline, no problem. It's just I didn't have time to look at this paper. I was organizing other sessions. Sorry. Please go ahead.
Yeah, I think Sebnam, probably you're asking about the water security. So there is a competition between, there's a competition for water between different sectors. So
where's the environmental component? You know, normally we leave some water for the nature to regulate itself. Is this the idea here? This is my, question, but it's not important. We can discuss it after the session.
It is important because you see those water being saved where it goes. So if it goes some competitive uses, you're not really helping improve the water security or environmental security. Yeah. So that's because we do see a larger portion of the water being diverted to residential uses, industrial uses, not going back to the nature. So I think that's what Sebnem is asking. Thank you for the question.
Thanks.
And yeah, we still have time for Fazar.
Thank you. I have several questions. Let me ask one by one as time allows. So the first question is, what's driving the total factor productivity? Is this endogenous or it is a shock in the model?
Okay. Can you see the questions again?
So you have total factor productivity, right?
Yeah.
So what is the source of change in total factor productivity? Is this investment? What's driving the change in total factor productivity? Is this exogenous shock to the model, or it is an endogenous variable in the model?
It is endogenous. TC is implemented endogenous in this model.
So this means that if that's endogenous, then some variables are explaining the expansion in total factor productivity. Can you explain what are those factors?
Do you mean what triggered the TFP growth?
So, for example, one reason could be using more fertilizer, for example, or multiple cropping, using more multiple cropping, using a better seed. What is driving total factor productivity? A new technology could come in. So what are those?
In this model, we implement TC endogenous by related the TC into the factor costs. When the technology is already high, the costs to trigger the technology improves will be needs more. So that's why the TC is implemented endogenous in this model.
I think mainly technology. So I know Chinese government is implementing a large investment to improve the productivity in rural production. Some of the sectors crops already using very intensive inputs like fertilizer and water, but machinery investment probably another factor behind it. Because previously lots of the small farms are using labor-intensive farming, but now more machinery is available.
Yeah. So okay. So I think it's important to explain what are the source of those total factor productivities. If that's based on actual observations. Is this a theoretical framework? What is that? I think it's important to highlight that.
Yeah.
So, and the improvement in water use efficiency could be a source of total factor productivity, for example. It's important to explain all of those. So the other question that I have, I'm going to stop after that. So have you considered the change in crop yield when you, due to climate change in this practice?
Consider land use change?
No. Change in productivity of crops due to climate change.
Oh, no, the climate change is is that not influence in this model?
So I think it's important to consider what would happen to crop yields due to climate change and the interaction with water scarcity. These are important topics.
Yeah. Okay.
Yeah.
Thank you.
Very good
Thank
comments.
you very much.
Yeah, I think Ruiying, you got very good feedback from the audience, and those are very useful. Thank you all for the questions. And our next speaker is Srabashi. Srabashi, are you ready?
Yes, ready.
Yes. Srabashi will present some very recent work she's doing to look at the impact of conservation policies on the labor market. The floor is yours, Srabashi. Go ahead.
Okay. Thank you, Jing. This is work that we are doing with Iman and Dr. Hurtle, and essentially we are trying to model agricultural markets and in order to evaluate environmental sustainability policies in the context of integrated assessment models. So here's a brief outline for this about 20-minute talk. I'll first talk about the motivation and the contribution of this work, delve deeper in some detail into the theoretical model under two different assumptions, describe the quantitative model, propose this new model that we are developing in this paper called the Simple G Commuting Zones model. So that's what CZ stands for. Just briefly go over some results and conclude with where this research is headed next. So this entire work is kind of grounded in the context of integrated assessment models. These integrated assessment models, or IAMs, are very well placed to evaluate environmental policies because they are they consider both socioeconomic outcomes as well as environmental outcomes, and also the impact of policies which can perturb any of the different variables in the interaction between socioeconomic and environmental outcomes. So they are very well placed to evaluate environmental policies. However, it is important to understand how agricultural labor markets are modeled in IAM models. Ruiying spoke about one of them, the MACPI model, and as well as the Simple G model. In both these models, labor is clubbed under other inputs, and the assumption assigned to this broad group of other inputs, which also clubs together, I think, fertilizer, chemicals, and stuff like that. The assumption assigned to that is that all the inputs clubbed together under other is perfectly mobile, and it is very easy to kind of move all these inputs from one point of production to another point of production geographically, as well as it is costless to hire or fire. That also implies in terms of labor that it is costless to hire or fire agricultural workers. And in the next slide, I'll talk about why that assumption might not hold up anymore. Another example of IAMs is the GLOBIOM model, which focuses on land and water explicitly and does not delve much deeper into labor inputs, so does not really model impacts on employment, impacts on wage changes due to environmental policies. And a fourth example is the MIRAGE model, which does explicitly model labor, but it is designed at a very aggregate scale. So why do we need to focus on agricultural labor markets in the context of IAMs? So first of all, there is an intrinsic importance for delving deep into the quality of life of agricultural workers who grow our food, and so the employment changes, wage changes have intrinsic importance for us to understand what happens to employment and wages of agricultural workers as environmental policies are implemented. But even beyond that, labor is a critical input to agriculture for some crops such as fruits, vegetables, etc. The cost of labor in gross farm income can be as high as 25 to 35%. So it is an important input. Any changes in agricultural labor as a whole could have significant impact on agriculture productivity, etc. What is produced, where it is produced, that kind of stuff. Next, the structure of agricultural labor markets has been evolving in the past few decades. In the past 2 decades, at least, there has been increasing labor shortages, which is one way of sort of quantifying that is this graph on the right hand side, which shows that there is a steady increase in farm workers' wages since the 1990s, and in the last decade, it has only continued to steadily increase. More recent studies which have tried to estimate the farm labor supply elasticity have shown that agricultural farm labor supply is relatively inelastic. So the numbers that these studies have come up with ranges between like very close to 0 to 1 to 0.8. So that is a very compared to the assumption embedded in the IAMs that I was describing before, which is the perfectly elastic labor supply assumption, where the number 0 to 0.8 is assumed to be infinity. So that assumption underlying these IAMs does not hold up in the recent experience of agricultural labor markets. So the consensus in the literature is pretty significant that there's an end of an era of labor abundance. So we really need to better understand the interaction between agricultural. We need to better model agricultural labor markets and better understand the interaction between agricultural labor markets and impact of conservation policies, which directly impact the agricultural sector, because conservation policies, the ones that we will talk about here, are mainly those that target water conservation or land conservation. So given that motivation, in this paper, we developed a theoretical model for the interaction between agricultural labor markets and conservation policies. And using this theoretical model, we can delve deep into the impact of conservation policies at a very fine spatial scale. In this paper, we look at a 5 arc-minute spatial scale, but it can we take that because that is the standard in several IAMs, but it can be defined as whatever is suitable to the researcher. Next, in this paper, we evaluate how does relaxing the perfectly elastic labor mobility assumption impact the outcome of conservation policies in rural communities. So we look at outcomes such as weight changes, employment changes, how much land or water or irrigated land is actually conserved, stuff like that. And finally, we propose a novel model called the Simple G Commuting Zones model, so CZ model, building on the existing literature, and I'll describe that in more detail next. Okay, so next I'll talk about the theoretical model, and again I'll talk about it under 2 different assumptions, where output prices are endogenous versus a second case where output prices are exogenous. So first, looking at the case where output prices are endogenous. So in this case, think of this model as relevant at a national level, where if there are some production changes at the country level, for example, the United States, if there are some if the shock is large enough, if the conservation policy shock is large enough for the United States, there might be a change in output price, which is important to model in this case. So think of the endogenous output price case as a national model, and I'll talk about the exogenous output price case a little later. So this model is a 2-input partial equilibrium model. We have 2 inputs, and we disaggregate that into labor and all other inputs, which I club under irrigation augmented land, which includes land, water mainly, as well as other inputs such as fertilizer, etc. Both these inputs, L and A, have an input supply elasticity indexed by VI. I refers to L or A. And sigma refers to the constant elasticity of substitution between the aggregate inputs L and A. So given these 3 parameters, sigma, VL, and VA, sigma, VL, and VA, we are able to characterize the aggregate supply curve of the agricultural sector. And on the consumption side, we just need the slope of the aggregate demand curve to set up this model where the aggregate demand curve interacts with the aggregate supply curve, and we have an equilibrium price and quantity. So given this framework, the way we implement a conservation shock is we implement a leftward shift of the aggregate supply curve, which is, so phi A is the conservation shock. Let's assume it is a shock which restricts cultivation in a limits water use or restricts cultivation in certain parts of the country. So that essentially is a backward shift in the supply curve of A, which leads to a backward shift in the aggregate supply curve, which we see here in this lower graph here from QS. The aggregate supply curve moves to QS prime, and we have a new equilibrium price and quantity, P double star and Q double star, and the change in the equilibrium price and quantity is lowercase p star and q star. So given this structure, we can use this structure to analytically define the quantity of the analytically understand the p star and q star. As expected, as a result of a conservation shock, crop prices increase and production decreases. And the capital gamma and the phi are all positive terms, so the production decreases because eta is also positive. It has all these three parameters are positive with a negative sign, so there's a decrease in q star and there's an increase in p star. We can use the same structure to investigate the change in input markets. So the two figures on the left-hand side characterize the output market, but we can use the same structure to better understand the input market. So in the input market, if we look at wages, employment, rent, and resource use, then we see that this important parameter VL, which is in the denominator as well as the numerator in some cases, shows up. Therefore, the labor supply elasticity parameter, which is VL, interacts with the input substitutability parameter, sigma, and the demand elasticity parameter, eta, to determine the impact of a conservation policy on different stakeholders. So we need to get a better hold on the VL parameter, given the evidence that I showed before that agricultural labor supply elasticity has been declining in the recent decades. So if I summarize the impact, summarize how VL interacts with sigma and eta, I just do that in this table instead of going into each of the equations. So it depends upon two different cases, one where sigma is greater than eta and another one where sigma is less than eta. When a conservation policy is implemented, agricultural producers can respond on two different margins, the intensive margin as well as the extensive margin. The extensive margin is when some agricultural land is restricted from cultivation. So producers bring in other agricultural land or other water sources into production, which was previously outside the agricultural sector. So that is the case when sigma is less than eta. And in this case, food price increases. There is an increase in food price, but there is a reduction in agricultural wages and employment as a result of the conservation policy. But if VL, the labor supply elasticity, is really small, then the increase in food price might get dampened. So consumers might experience a smaller increase in food price. However, the decrease in employment is also dampened. So fewer workers lose their jobs. On the intensive margin is when some of the land is restricted from production. So producers manage or use more inputs on the land that is available for cultivation. So whatever land remains in cultivation is more intensively managed. So that and we characterize that case as sigma is greater than eta. In this case, also there is an increase in food price. However, there is also an increase in agricultural wages and employment. So you can see under these two different assumptions, how agricultural workers are impacted is different. And then if the labor supply elasticity is smaller, as we have seen before, in this case, the food price increase is magnified. At the same time, the agricultural wage increase is also magnified. However, fewer workers are able to enjoy the magnified increase in wages because the overall increase in employment is dampened. So all this table essentially argues that we need to better understand the VL parameter, which is what this paper is aiming to do. Next, so this this theoretical framework is designed assumes that this P star is endogenous in the model. However, that is relevant when we are looking at a national level model. But if we are looking at a really disaggregated, fine scale, let's say a single producer or a group of producers in a small geographical area, such as 5 arc minutes, which refers to about 6 to 8 square kilometers of area, then we can assume that the P star, the output price is exogenous, because changes in a geographically small area of land might not have a significant enough impact on the national market, and therefore the P star might be constant for the P star might be constant. There might be no change in output prices. So why is that important? Why is that important? How is that relevant in empirical analysis? So for example, here I have two different environmental issues, examples of environmental issues. On the top here is the case of nitrate leaching, which can be targeted by retiring land into wetlands. So as you can see, all of the United States is not going to be impacted by this, but some specific grid cells or some specific groups of agricultural land is certainly going to be impacted pretty significantly. And in the bottom here shows the issue of groundwater scarcity. So the grid cells that light up in red and orange are where groundwater extraction is much higher than groundwater recharge. So again, if we implement a groundwater conservation policy, it is likely that we will be targeting these specific grids and not the entire country as a whole. So this is where it is important. It would be useful to assume exogenous change in output prices and delve deeper into these specific grid cells. In doing so, we are also able to disaggregate the impact of the conservation policy into where phi is equal to 0. So all these blue grid cells or all these gray grid cells where the policy is not implemented directly. And in that case, we see a rise in resource rents, rise in agricultural wages, and rise in employment. And that is essentially because as the policy impacts some of the grid cells, some of the production from the directly impacted grid cells moves to the other grid cells that are not impacted directly. So production moves to the other grid cells, and therefore there's increased pressure on land resources, labor resources, etc. On the grid cells that are directly impacted, what happens as a result of the conservation policy depends upon this condition up here. So the term in the brackets can be interpreted as a total supply response relative to the magnitude of the conservation policy shock. So if the total supply response is smaller than the conservation policy shock, then there is still an increase in resource rents. However, if labor supply elasticity is smaller, then that resource rent increase is magnified compared to the other two cases where the resource rent increase is dampened. So again, this goes to show that we really need to get a better handle on the labor supply elasticity parameter, which are often ignored in integrated assessment models as they stand now.
We got about 2 minutes.
Okay, great. So I think I'll skip, I'll talk about this is the Simple G framework. I'll skip this and I can go into more detail if there are questions. So we propose a Simple G commuting zones model where we essentially disaggregate, which builds upon the Simple G model previously published in in Baldos et al. 2020. In there, we disaggregate labor and non-labor inputs, and we impose a commuting zone structure to build in some immobility in labor, contrasting previous work where labor mobility is considered to be perfectly elastic. And then we design a policy. We kind of motivate this policy because based on groundwater scarcity. So the grids that light up on the left hand side are targeted where groundwater extraction is limited at the recharge level. So the results from this section, I'll just skip the national level results. The national level results are not that interesting, but when we look at more grid specific results, there is a irrigated crop production nationally could increase by minus 0.6%, but regionally, specifically the grids that are targeted, it could be as high as 66 to 45%, as well as employment, it could be a fall by 20 to 45%. But one of the main observations here is that if we assume labor mobility is perfect, we implicitly assume that there are no wage changes. But if we build in labor immobility, then we see that some commuting zones where the policy is directly targeted, wages could fall by 20 to 35%. I'll skip that and I'll just talk about disaggregating the changes in employment using this using the theoretical framework that I sort of described before. So on the left, on the first graph here is the change in employment as we see from the model results. And using this equation here, we can disaggregate that into the changes in the extensive margin, intensive margin, and the policy shock. And as you can see here, some of the grids, as a result of the policy shock, some of the grids that are directly targeted actually see an increase in employment. And this framework that we are developing here is able to explain why, because the extensive and intensive margin response, which is together described as the total supply response, offsets some of the policy shock that is shown in the last graph on the right hand side. So this, however, the grid cells where the color is red or orange on the left hand side, on the first graph on the left hand side, there the extensive and intensive margin response is not able to adequately offset the conservation policy shock. And again, as you can see here, the capital gamma L is a function of VL. So VL is an important parameter that goes into how much would be the extensive margin response, how much would be the intensive margin response, and is it able to offset the conservation policy shock. So all this is essentially to drive home the point that VL is an important parameter that is overlooked, but in this work we are trying to model it more explicitly. So just quickly to conclude, the simple framework is really useful in kind of keeping the economics tractable to understand the grid level results that we observe from IAMs. At the same time, delve deep into understanding the impact of the policy, as I showed by disaggregating the results of a conservation policy. We make the point that labor markets, understanding them is important because their structure is evolving, and depending on the assumption we make about labor markets, it can have a divergent impact on different inputs of production, for example, labor and resources. We would be missing the potential wage impact of conservation policies if we don't take into account the structure of labor markets. And finally, this is work in progress, is the theoretical framework that I proposed can be used to contrast, can be used to actually clearly show when under what conditions the impact on labor and resources over or underestimated. Thank you.
Thank you. It's very interesting to look into the impact of labor, which is, as you have shown, often ignored in other models. Mm-hmm. Yeah, we have got one question from the
Alla.
chat.
Oh,
and then Alla.
Okay, let me read the question. Does irrigation augmented land mean that water input is modeled as an implicit factor of production? So the first, I'll just go one by one. So the first question, irrigation augmented land, water input is modeled as an implicit fact. So essentially, I skipped a bunch of stuff. So in the in the in the production tree, land and water are kind of substitutes. So the idea being that you could more intensively manage land by using more water, and I can go back to the production tree. But when I talk about irrigation augmented land, essentially that's aggregated up in value terms at the as I go up the production tree, I aggregate the input. So the irrigation augmented land kind of in value terms is a sum of land and water, if that makes sense. So here, as I go up in the tree and I talk and my model stops here, it takes both land and water together, my theoretical model. But in the simple G commuting zones model, the land and water inputs are separate and they are substitutes between each other. Do you observe quantity volume of the irrigation? Yes, I think we do. And this is more Iman, my co-author Iman's fort. So he delves really deep into the data that goes into the simple GCZ model. How is labor modeled? How would you go about identifying the substitutability between them? Okay, so so labor goes into the non-land inputs. So kind of labor is a substitute. Labor is a substitute between land and water. So again, the idea being you could use more, you could manage your irrigation, manage the irrigated land with more non-land inputs that could come from labor as well as fertilizers, etc., as well as capital or fertilizers, etc. So that is the substitution kind of structure that is built into the model. Hope I answered all of them. Let me know if not.
Yeah, you can interact offline, and Alla is the next raising the hand.
Yeah.
Yeah, Srabashi, thank you for
Hi.
the presentation. Hi.
Thank you.
Do you make assumption about length of run? You presented specific case, right? What is the length of run in the specific case, conservation policy? So what is the period of time, length, period of time?
Yeah. So I skipped a bunch of that. So this is the policy gets implemented in 2050, and this is in 2050 we implement a counterfactual where this conservation policy is implemented. So from right now, I guess I think 2016 or 2020, the data is based on one of the current years. We simulate the population growth, income growth, TFP growth in year 2050, and we evaluate what happens to all these outcome variables, employment, wages, etc. And then in that 2050 scenario, we implement the conservation policy where water extraction in these grids is limited, and then we compare the two.
Yes, so my question, in 2050, what is the length of run? How quickly your conservation policy come into effect?
Oh, instantly, yeah. So this is
instantly.
Just a model
it's
simulation.
A short run. It's a short run, right? Is it short run?
Yes, yes.
So my question, follow-up question is, the presentation highlights importance of this labor supply elasticity, right? And how importance of this parameter change when you change the length of run? I understand it's critical when it is very short run. So when you go longer run, is it important? Will it be like less important when you increase the period of adjustment?
So I guess that takes into account the way the agricultural labor markets have been evolving, and how it is evolving, and what we foresee in the future. So from what I understand from the agricultural labor literature is that agricultural labor was much more mobile before, but now it is increasingly getting scarcer and scarcer, and that's a trend that is kind of relevant worldwide. So if it is as we move in towards 2050, agricultural labor is likely to be more scarce. But I guess what you're saying also implies how long agricultural, like producers, have time to adjust to a conservation policy. But if agricultural labor markets are becoming like stricter and stricter, then if labor mobility continues to be continues to fall, then the importance of this parameter is only going to increase or going to remain, even if producers have a longer time to respond to it, if that makes sense.
Thank you. Yes, I think something to think about.
Yeah.
It seems like there are two lengths of run.
So like different assumptions for short run and long run adjustments to a conservation policy, you mean?
Yeah, maybe. Yeah, something to think about. Thank you.
Yeah, okay, thank you.
And the last question goes to Fazard.
Thank you. Nice work and nice presentation. So let me be a little bit more specific. What elasticity of substitution have you selected for this practice?
So I think it is 0.5 or 6.
Okay, so this is a small one, right?
Yes.
So, and I assume it is applied to all grid cells, right?
Yes.
So, and probably you know that that's a very diverse parameter across the United States. So in some states versus the other, that elasticity of substitution could be very different.
Yes. I did say that it's the same across all grids. I think one of these is the same across all grids. So I think sigma n is the same across all grids. I'll have to look if sigma O is also the same across all grids.
So I assume they are the same. That's the principle that all grid cell models are following, because they do not have estimates for elasticity of substitution across grid cells. So I think you need, when you go to regional effects, you need to carefully discuss that.
Yeah.
For example, California versus Midwest. That's something that you need to take care.
Yes.
So the other thing that I have, the conservation policy could be very different, right? In the United States, somehow, we use CRP land, for example, right? So in some other countries, like other regions, like EU, so the policy could be go on fertilizer, ban on some types of fertilizer, and those are probably behave in different ways.
Yes.
So, and you need to take into account that factor as well. So the other thing, just a comment for you, is that if I understand correctly, the simple model is just one crop.
It's an aggregate crop, yes.
Yeah. So, and that's very important, because the policy could change the mix of crops.
Yes.
So, and when you're talking about that, the mix of crops, irrigation for different types of crops, those are important things to consider. So in your work, you need to highlight those and address that those are important facts that is missed in Simple G.
Yeah.
Thank you.
Yeah. Okay. Thank you, Prasad.
All right. So our discussion is supposed to end at 07, but Subnam still posted a question in the chat. If Srabashi could quickly address.
Yeah, very briefly, formal versus informal. Does it include it in your thinking? Thanks.
So labor statistics is from USDA. That's again, I don't have all the data information at the top of my head. It's kind of Iman's forte. But do they account for formal versus informal labor? Yeah. So does small labor supply elasticity hold for season? So yeah, so the last question first, some of the next the next steps in this work is to disaggregate labor into different types of labor, just exactly like you highlight seasonal, undocumented versus family labor. The mobility between between those two different groups is certainly going to be different. So that's something that we add another layer to the production tree that I discussed. So this kind of aggregates all of them and assigns the same supply elasticity to all of them, which is a huge simplification, but that's where we are right now. The next step is to do exactly what you're saying. And do they account for formal versus, yeah, and in the data, I don't think they take into, so in the US context, I guess it would be family labor and hired labor broadly. So all the seasonal workers, etc., would be hired, and the other one would be family. I think we impute the value of family labor and add it in there. So there is some representation of kind of formal and informal work. Yeah, but very relevant questions, very relevant for what we are doing next with this. Thank you very much.
Thank you.
Great discussion. So next presenter is Alla. We'll talk about the transboundary water challenges and potentials. Alla. Yes, it looks good.
But it's not my first slide. I wonder how I cannot move up and down. No, why?
Can you use left and right to move it up and down?
Wait, let me try it again.
Mm-hmm. Yep.
But it's not full screen here, right?
Yeah, we can still see it. If you can advance it, that's okay.
I cannot move. For some reason, I cannot move. Oh, okay, I can move it now. Let me do full screen.
Looks good.
Yeah. Okay, yeah. Okay, thank you. Thank you for coming to the session. Our title of my presentation is Transboundary Water Challenges and Potential Collaboration in the Tigris Euphrates River Basin Water Management. This ongoing work is conducted in collaboration with Iman Hakiki, Amit Karimi, Exanreza Sajedinia, and Farzad Tahiripur. And I think Farzad is here in this meeting with us. Financial support is provided by the World Bank. Today, 47% of the global population live in areas that suffer water scarcity at least 1 month each year. And by 2050, this share will increase to 57%. Globally, transboundary rivers carry almost 60% of fresh water flows and are crucial in ensuring people have adequate water supply. Blue Peace Index, constructed by the Economist Intelligence Unit, examines the extent to which countries are managing their shared water resources in sustainable, equitable, and collaborative manner. The index examines 30 countries across 7 selected transboundary river basins using various qualitative and quantitative indicators. These river basins are shown on this map, and of the 7 river systems ranked by how well countries manage transboundary water resources, the Tigris Euphrates River Basin has the lowest score. The 2 rivers, Tigris and Euphrates, and their tributaries run mainly through Turkey, Syria, Iraq, and Iran. Turkey has the largest reserves of renewable water among these countries and control over the flow to the downstream countries due to the construction of dams. The situation in the basin is particularly difficult due to climate change, weak cooperation among riparian countries, intensive hydropower development, inefficient agricultural practices, and political instability. Ongoing construction of dams and hydropower plants and projected increase in water use by Turkey and are major concerns in downstream countries, particularly in Iraq and Syria. At the same time, by mid-century, climate change may result in a 20% reduction in rainfall over the river basin, and the availability of water for irrigation may decline by between 13 and 28%. The objectives of the study are to quantify the impacts of climate change on water scarcity by 2050 in the Tigris Euphrates river basin and other river basins within the Middle East region under alternative climate futures, to evaluate economic outcomes of these changes in water availability, and to evaluate cooperation plans that can be implemented to reduce controversies over water allocation in the Tigris Euphrates river basin. Overview of the methodology. We use projections of future temperature and precipitation produced by general circulation models. These projections are inputs into hydrological model. The hydrological model projects water scarcity given climate scenarios. Then comparative static computable general equilibrium model, GTAP BioW, is used to quantify economic implications of changes in water supply. Let's talk about the economic model. GTAP BioW model combines economic and biophysical information on land and water at the spatial resolution of river basin agroecological zone in each region of the model. Iran, Iraq, Jordan, Lebanon, Syria, Saudi Arabia, and Turkey are separate regions in the model. Other countries are grouped into the rest of the Middle East and the rest of the world regions. Water is modeled as an explicit input in irrigated crops, livestock, and water utility services. Water utility services then supplying water to other sectors and the final demand in the model. The three activities compete for water at the river basin level. Individual crops compete for water within river basin AZ, and irrigated crops are distinguished from rainfed. Large river basin could serve several agroecological zones. This figure represents economic activities that use land and or water within a region of the GTAP BioW model. Within each region of the model, there is a national competition among industries for labor, capital, and resources other than land and water. Land in each region of the model is split into agroecological zones, and competition for land within a given AZ across users is constrained to include activities that have been observed to take place in that AZ. Within each AZ and region, land is allocated to crops, livestock, and forest. And within cropland, land is allocated to irrigated crops and rain-fed crops. Land can move from rain-fed to irrigated and vice versa, if biophysical and economic factors allow for such conversion. At the national level, irrigated and rain-fed crops farms supply a homogeneous but region-specific product to domestic and foreign consumers. To incorporate water in the model, each region is divided into several river basins, and each river basin serves several agroecological zones. Supply of managed water in each river basin and region is exogenously specified, and agricultural and non-agricultural industries within the region compete for managed water at the river basin level. Water does not move across river basins, but it can move across AZs within a given basin and region. Now let's talk about how water is supplied to different activities. So we assume that water cannot move freely across users within river basin. To incorporate this assumption in the model, supply of water to various activities is represented with nested constant elasticity of transformation structure. There are 3 levels in the structure. First, in the very top, water is allocated to agricultural and non-agricultural uses. And in the second level, water is allocated to IZs for crop irrigation and aggregated livestock sectors. So these are in the same level. Then at the very bottom of the tree, water can move freely across irrigated crops within each agroecological zone. And similarly, water moves freely among non-ruminants, ruminants, and dairy sectors within aggregated livestock sector. There is a market clearing condition for water within each agroecological zone and within aggregated livestock sector. Now let's talk about hydrological model. The hydrological model is based on water balance model, originally developed at the University of New Hampshire. The hydrological model is a global model that simulates both the vertical exchange of water between the ground and the atmosphere and the horizontal transport of water through runoff and stream of networks at the grid cell level. Among inputs in the hydrological model are daily temperature and precipitation and harvested area and non-agricultural use of water by country. Given the harvested area, the model produces irrigation requirements to maintain agricultural yields in response to water stress in the future climate. And model also tells us how this requirement is met by withdrawals from surface water, shallow groundwater, and deep or unsustainable groundwater. And with less precipitation, less surface and shallow groundwater will be available, which will be compensated by larger withdrawals from unsustainable groundwater. Climate projections. These are inputs into the hydrological model. Daily temperature and precipitation variables are critical inputs in the hydrological model to project the availability of water resources in the future. We use 2 data sets to obtain projections of these variables. First data set is constructed by our colleagues Boyka, Reggiani, and Tadini using temperature and precipitation time series from 1979 to 2100, produced by 19 general circulation models under coupled model intercomparison project phase 5 for 2 climate scenarios, RCP 8.5 and RCP 4.5. These series are mutually weighted and bias corrected using ERA 5 reanalysis data from 1979 to 2005. And I will refer to this data set as an ensemble. The second data source is next GDDP CMIP6. This is NASA Earth Exchange Global Daily Downscale Projections Phase 6. So next GDDP CMIP6 dataset. It has contained global downscaled climate scenarios derived from GCMs, and dataset compiles climate projections from 35 CMIP6 GCMs models for 4 SSP scenarios for the period from 2015 to 2100. And ideally, we would like to run the hydrological model with each GCM output. However, this would require very large computing resources. So instead, we systematically compared GCM with historical observations to evaluate GCM's performance on precipitation metric for the Middle East. We found MIRAC model performs somewhat better than other GCMs. So we have 2 climate data sets, next GDDP CMIP6 and the ensemble. And from each climate dataset, we use 2 climate scenarios. From next GDP CMIP6 dataset, we use MIRAC, temperature and precipitation, under SSP5, 8.5, and SSP2, 4.5 scenarios. And we use ensemble temperature and precipitation constructed using CMIP5 output under RCP 8.5 and RCP 4.5 scenarios. And in this talk, I will present results based on high emissions scenarios only. This figure shows projected cumulative annual precipitation for Iran, Iraq, Syria, and Turkey based on output of MIRAC model under SSP5 8.5 scenario. In Turkey, yellow line here, you can see that Turkey receives more precipitation than other 3 countries, Iran, Iraq, and Syria, in the Tigris Euphrates river basin. And this will continue until 2050 with some downward trend for all countries seen on this figure. So now let's talk about the results. Let's start from hydrological model results. These are based on MIRAC temperature and precipitation, shown in blue, and results based on the ensemble are shown in orange. Changes in water supply are shown by country and by river basin. So projected reductions in water supply and variance across countries and river basins are larger with MIRAC than the ensemble, and the difference is quite large. The differences are especially large for Iran and Turkey. With MIRAC projections, the hydrological model predicts that Iran will experience the largest relative reduction in water supply, reaching almost 40% in Western Asia, Iran river basin by 2050. Results based on the ensemble suggest that Turkey will experience the largest relative reduction of 12% in the Tigris Euphrates river basin. Overall, results based on MIRAC and the ensemble agree that Iran, Turkey, and Iraq will experience larger relative reductions in water supply than other countries and basins, and Lebanon seems to be the least affected. Now, same results, but now we focus on Tigris Euphrates river basin only. And within this river basin, the largest relative reduction in water supply is projected in Turkey, almost 35%. And now let's talk about the scenarios. So scenarios that we implement with economic model. Reductions in water supply projected by the hydrological model are implemented in GTAP BioW. Note that in the CG model, the reduced water availability affects only irrigated crops and would give an advantage to rain-fed crops relative to irrigated. This, however, should not be the case, as rain-fed crops will get less rain in the future, according to the climate projections. Another effect of warmer climate on both irrigated and rain-fed crops is changes in crop yields. To represent the impacts of climate change on crop yields, we implement changes in total factor productivity in both rain-fed and irrigated crop sectors. So in the next slides, we will look at the results from 4 scenarios simulated with economic model. The scenarios are changes in water supply driven by MIRAC model, SSP5 8.5 projections, without changes in crop yields, and then with changes in crop yields. So these are 2 scenarios. And then the other 2 are changes in water supply driven by the ensemble RCP 8.5 projections, without changes in crop yields, and then with changes in crop yields. Before we look at the simulation results, let's talk about the size of agricultural sectors relative to GDP in the Middle East. Overall, output of agricultural activities relative to GDP is small. Share of agriculture in GDP is the largest in Syria, 22%, followed by Jordan, 13%. In Jordan, however, livestock sectors play a larger role than crop sectors. Crop sectors as share of GDP are largest in Syria and Iran, and comparison of yellow and blue columns shows that most of the crops in the Middle East are irrigated.
2 minutes, Alla.
Oh, okay, because of the dry climate. So these are changes in crop output by crop and country in the 4 scenarios. And these figures show results based on Marek projections. The top 2 figures show results based on Marek projections, and bottom show results based on ensemble. And first column shows only water scarcity, and second column shows both water scarcity and changes in yields. So reduction in water supply under mirror climate projections are larger. For this reason, overall, reduction in crop outputs are larger in the top 2 figures. Under mirror projections, reduction in crop outputs due to reduced water supply are largest in Turkey. We assume that rice, wheat, and coarse grains yields will drop under warmer climate, and yield reduction will be larger for rain-fed crops. For these crops, combining reduced water supply with reduced yields further reduced crop output. In Turkey, wheat output will drop by more than 40%, and overall, in this scenario, wheat is the most affected crop. Changes in food consumption quantities and prices and crop import quantities from the rest of the world by country scenario shown on the slide. Food prices increase strongly in the Middle East. Highest increases are observed in Iran, Turkey, and Syria, and Iraq. In Iran, prices may go up as much as 18%. Food consumption may fall by 2-3% in these countries. The reduction in domestic crop output is compensated by a large increase in imports from the rest of the world. In Iraq, crop imports may increase by more than 40%. But keep in mind that for some of the crops in the initial database, imports in Iraq are small. So it's a large increase starting off a relatively small number.
We're running out of time. If you quickly wrap up. Yeah.
Yes, so this is my last slide. The goal of the study is to quantify economic implications of the impacts of climate change on water scarcity in the Tigris, Euphrates, and other river basins in the Middle East region. We find large range of reductions in water supply in the Middle East region between 3 and 39% by 2050, depending on the river basin and country. And within Tigris Euphrates River Basin, the largest relative reduction in water supply is projected in Turkey. Among crop sectors, wheat output decreases the most. Crop imports by Middle East countries increase dramatically because of the reductions in domestic output. And our next steps is to look at the RCP 4.5 scenario, combine climate impacts with increases in upstream countries' water withdrawals within the Tigris Euphrates River Basin, and consider cooperation plans that can be implemented to reduce controversies over water allocation in the Tigris Euphrates River Basin. Thank you.
Thank you, Alla. Yeah, so we have already got some questions from the chat. If you want to read it, or if you want to interact with the person who asked the question.
So I see a question from Anton. May I ask if there is such a concept called transport of water across river basins as these regions in the GTAP BioW model? So this the transport of water is something that will happen in hydrological model. And unfortunately, I should say that Iman is the best person to answer this question. So if this happens, so essentially the supply of water within country and a basin is given for the CG model. Any changes to these variables should come from hydrological model. And if there is a transport, then I would transport in the hydrological model, then I would think that there may be cases when there are increases in one place of water use, of withdrawals, and there are decreases in another place. And this all should come from hydrological model. Then there is a second part of Anton's question. Does the model capture the friction in terms of the cost of delivering effort varied by distances, or the water movement across different categorical, or the water movement across different categorical AZs regions? So if I understand correctly, in the hydrological model, there is no such thing as a cost. It's either here or there or not there. I don't know if there is an option to build a new channel. I don't know, but I don't think there are costs. In the economic model, well, we have built this CT structure that should make water movement more costly. However, within an ecological zone, within the country and the river basin, and focusing into the ecological zone, across crops, we move it freely. And so there is no cost to this, no.
Yeah, because of like my hydrological background, like whenever I look at these economic models involve water, I always wonder like how do we get the water, like where it comes from, like so it seems like in the GTAP Biomodel model, there's a physical account outside in the hydrological model, and then in the GTAP model, we treat it as a endowment, free endowment. There's no friction for getting the water, no matter how and where it comes from.
So may I make a comment here?
Go ahead.
So basically in the GTAP BioW, water has a price. This is an endowment, but it has a price. It's not free. Okay. So the supply is the total amount of available water is fixed, but it has a price. So this means that if you need to increase the endowment, then you have to do it due to a shock. Okay. So in terms of moving water from one river basin to another river basin, it is not difficult to simulate with the GTAP BioW. However, at this point, we do not consider that. So, but as Alla mentioned, the movement of water from one application to another application is restricted, meaning that it's costly due to a small transformation elasticities that we have in the model. So this is a brief explanation that I could offer you.
Right. So the prices are captured outside the GTAP model, right?
So when the GTAP database is constructed, due to the construction of the database, the yield premium due to irrigation is assigned to the price of water. So we compare rain-fed and irrigated. An additional yield is assigned to irrigation, and that in that way we determine the shadow price of water in that model.
Okay, I saw two more questions. I think we should give them some questions. The second question I saw is in chat. It's Mohammed.
Yes, I can read the question. Does your hydrological model consider the impacts of construction, filling, and operation of storage dams? Again, this is a question to Iman, but I think so in his model allows to replicate something like increased water withdrawals. I don't know if he can identify whether it's because of the dam or other reason, but yes, he can model increases in water withdrawals from the river stream.
So again, I need to make an additional comment in addition to what Alla mentioned. So the hydrology model has, in its baseline, has information on the existing infrastructure, dams or water canals, and those kind of things are built in the database. So it's a part of the database in the water model. However, due to the simulations for this work, we assume those are not changing. So the infrastructure will remain the same due to simulations.
And there is a second part. Do dams play a role in the spatial and temporal distribution of water resources across Tigris Euphrates Basin? It's built, the initial, what is observed in the initial period of the analysis built in the hydrological model, but we don't change this in the scenarios. And there is another question. Oh, no, it's not a question, it's a comment. Yeah, you're welcome, Anton. Thank you for the questions. And Sebnem?
Sebnem, yeah.
Hello. So big fan of your research since years, and congratulations for the improvements since the last time we worked on the model with Farzad. Just my, and I will read the paper in detail later, but on the big picture, I got a little bit lost, and maybe you can clarify me now or later, coming from Turkey. So you are showing that Turkey is the country that gets the most rainfall, and the water supply on another slide is the one that is likely to decrease the most. So am I confusing maybe the terminology? Is the water supply available for agriculture? One question. And referring to previous questions on how the dams are used, my understanding and experience is that this big dam in Turkey, which is raising all this question, is mostly used for hydropower. So does this explain that there is less water for agriculture by design, but more for other uses? And the third one, I know a little bit the mentality at the World Bank. Do you take into account the political economy? Because there are historic water sharing agreements, and Farzad is the first witness. My understanding from the Turkish side is that they are still being respected, but there may be other realities that I'm not aware of because I left my country a long year ago. So over to you. We can discuss also offline. Thank you.
Yes, so on the slides that show, so Turkey, of the 4 countries in the Tigris Euphrates River Basin, currently today Turkey has largest precipitation, right? And it will continue to 2050, but with some downward trend. And in 3 other countries as well, the trend is downward. And it seems that this reduction of the precipitation, so may not be huge on the slide, it is sufficient to create very large reduction in water available in these river basins. So this is the reductions that I show is a reduction in water supply. The precipitation is still high, but it's higher than in other 3 countries and highest in this river basin, but it has downward trend. So for this reason, the supply of water is reduced. And also this supply reduction in supply, the shocks that we construct, they take into account that some of the water will have to come from deep underground. And we consider this as indication of water scarcity. So this is important. So less water on the surface, less water in shallow underground. More water must come from deep underground. And this is unsustainable and also costly to pump, right? So we consider this as an indication of water scarcity. Then, can you repeat your second question?
Dams.
The use of them for hydropower rather than irrigation purposes. And the third one is political economy, that there are treaties.
Yes.
Yeah.
So in the hydrological model, if I understand correctly, it does take into account existing dams and it takes into account current harvested area. So water scarcity that we measure, it's conditional on these parameters. And it does not change over the simulation with the hydrological model. So harvested area is fixed. All the dams are in place from now to 2050. And in the economic model, we don't, I mean, we just take this shock to the water supply, and it's mostly affecting water available for irrigated crops, livestock, and non-agricultural uses. So does it answer your question? Okay, on the political economy. So the motivation for the work, you look at the literature, the references that are listed in the paper, and there is a discussion that Turkey may increase water withdrawals because of the growing population, expansion of harvested areas, and there is also a kind of separate topic is construction of dams. And this discussion, this serves as the motivation for this analysis. However, I don't know if this discussion that we read in the literature, if they take into account existing treaties or not, and whether Turkey follow existing treaties or not. It may be the case that all this expansion of harvested area and future plans to expand dams, maybe it is within the current treaties. I cannot answer this one.
May I make a small comment here?
Yeah, final touch.
So I know that we are over time, but first of all, I would like to thank Shabnam for her contribution to this work. So Shabnam made a major contribution in developing GTAP BioW in earlier stage. First, we started with Jing, and then Shabnam came in. So when she was at the World Bank, we did some research for some part of the Asia, including India, Bangladesh, and those regions. And for your information now, the World Bank is following me to bring up that model again and do something for India. So in general, in terms of when we are looking at the case of Turkey, the simulation has been made in the water model, assuming the existing infrastructure will not change. So whatever is in the model in 2016, which is the base year, will remain the same. Harvested area will remain the same. So the simulation that we made so far is just the implication of climate change. What would happen with the climate change in terms of water supply? And then in the next phase, we are making simulations to see if Turkey withdraw more water. With respect to the political concerns, it is a major political concerns, as you know, well aware of that. So Turkey is very sensitive to this discussion. So the goal of this research is not to highlight what Turkey will do. The goal is to see if we can define a context of collaboration among the countries of the region to improve the use of water and improve the overall welfare of the region. So that's the goal. The political goal is that.
Yeah, if I may, it was also our message for the South Asian countries, right? Pakistan, India is as difficult as Turkey and neighbors. So I'm with you with that. Thank you.
Thank you.
Yeah, I would like to thank all the great presenters, and we have a small room, but the discussion is excellent, and thank you for your active participation, and thanks Ginger for hosting the session. Hope to see many of you in the rest of the meeting and enjoy the conference.